Hello, this is Mrs. Decker, and this is Objective 2B on specific heat capacity and calorimetry. So now that you know how to calculate heat transfer from one substance to another, we're going to use a calorimeter to determine the amount of heat flow between one substance to another. So before we get started with our calculations, we need to go over a little bit of vocabulary and how this will be set up. So calorimetry is the process of measuring the amount of heat absorbed or released during the chemical reaction. So calorimetry is the actual process of measuring the heat. A calorimeter is the device you use to determine the heat associated with the change, whether it's chemical or physical. Here are a couple of examples of calorimeters. You can use common things around the house. The first picture has a can of pop. That can of pop has a specific amount of water in it and the thermometer. And as you can see underneath here, there is something that is burning that is transferring heat from what is being burned to the water. So you're measuring the change in temperature of the water as you burn whatever substance you're burning underneath the can. The second one is a styrofoam coffee cup that again has a certain amount of water in it, and then you can put a hot object into the water, such as a metal, and measure the temperature change from the water as the heat is transferred from the metal to the water. These are examples of two things we will be doing in the lab, this unit. So here is our first example problem. 35 grams of an unknown metal is heated to 100 degrees Celsius. The metal is then placed into an insulated container of water. The mass of the water is 65 grams, and its temperature before adding the metal is 25 degrees Celsius. The final temperature of the system is 27.8 degrees Celsius. What is the specific heat capacity of the metal? So, in order to be able to do this problem, we have to understand what's really going on here. So to solve the problem, we're going to assume that all of the heat that is lost by the metal is gained by the water, and we can see that in the equation here. We have negative Q for the metal, that's the heat that's lost by the metal, is equal to the Q for the water, which is the heat that's gained by the water. Then you can substitute in the specific heat formula, the Q equals mc delta T, on either side of the equation to solve for your missing variable. So the first thing we want to do is list all of the information that we're given. So we have the mass of the metal, which is 35 grams. We have the initial temperature of the metal, which is 100 degrees Celsius. And we have the final temperature of the metal, which is 27.8 degrees Celsius. The heat capacity of the metal is what we're looking for. We know the mass of the water, which is 65 grams. We know the initial temperature of the water, which is 25 degrees Celsius, and we also know the final temperature of the water, which is 27.8 degrees Celsius. We also know the heat capacity of water, which is 4.184 joules per gram degrees Celsius. So now we're going to look at our equation. Remember, negative Q of the metal is equal to positive Q of the water. So for Q, we're going to substitute in mc delta T of the metal, and for the Q of the water, we're going to substitute in mc delta T for the water. So the left side of the equation will be negative 35 grams times C, which is what we're solving for, times the change in temperature, which is 27.8 minus 100. Now the right side of the equation for the water will be 65 grams times 4.184 times the change in temperature, which is 27.8 minus 25. So when you solve for C, you are going to multiply 65 times 4.184 times 27.8 minus 25. And then you will divide that by the negative mass and the change in temperature. So for C, you should get 0.301 joules per gram degrees Celsius. So make sure you check your math on this, that you can do it correctly, and get the correct answer for this before you move on. Sample problem number 2 says a piece of iron with a mass of 21.5 grams at a temperature of 100 degrees Celsius is dropped into an insulated container of water. The mass of the water is 132 grams and its temperature before adding the iron is 20 degrees Celsius. What will be the final temperature of the system? And you are given the specific heat capacity of the iron. Now you're going to set this problem up the same as you did the first sample problem, but the algebra is going to be a bit more challenging. So remember that the final temperature for the water and the metal is going to be the same, so you're going to be solving the equation for the final temperature. So we want to go ahead and write down all of our given information. We have the mass of the metal, which is 21.5 grams. We have the initial temperature of the metal, which is 100 degrees Celsius, and we have the heat capacity for the metal, which is 0.46. We have the mass of the water, which is 132 grams. We have the initial temperature of the water, which is 20 degrees Celsius, and we know the heat capacity of water is 4.184. So we're solving for the final temperature. So again, we want to take all of this information and we want to plug it into the equation. So you get negative 21.5 times 0.46, and we're solving for the final temperature, minus 100. Now for the water, we get 132 times 4.184 times final temperature minus 20. So now you have a variable on each side, but it's the same variable, so you need to go ahead and solve for that variable. So what you'll do first is multiply the 21.5 times 0.46, so that gives you negative 9.89 times final temperature minus 100. And then here you're going to multiply 132 times 4.184, and that gives you 552.28 times the final temperature minus 20. So now remember your algebra, you want to distribute on both sides. So you get negative 9.89 TF plus, because you're multiplying by a negative, 989 equals 552.28 TF minus 1145.76. Okay? So now move your like terms to either side of the equation. So you get 562.17 TF equals 12034.76, and then now just divide. So your final temperature for this problem is 21.4 degrees Celsius. So if you're having trouble doing this algebra, you need to go back and brush up, make sure you know how to do your order of operations and you're distributing correctly. The next page of your packet has a couple of practice problems for you to work on, and the answer key is posted on Google Classroom, so let me know if you have any questions.